Melhor. Um azulzinho.
Acho os dois iguais. Faltam os professores. Um minutinho. Dá 11h05. Hello. Hi, so we come back for this session. We have 3 short talks. First one will be from Ricardo Silva. He's a student here and also collaborator. And he'll be talking about updated bounds on the minimal left-right symmetric model from the LHC Dilepton resonance searches.
Okay. So, hi everyone, thank you for having me here. As Gabi said, my name is Ricardo, and I'm going to present about our work that we are developing for the current months, for the previously months, called Updated Bounds on the Minimal Left-to-Right Symmetric Model from LHC Dilepton Resonance Searches. Okay, so I'm going to start saying that the standard model is a very successful and well-tested model, but it has some features that can be further explained using extensions. So one of them is parity, which is in the standard model is explicitly broken, which is different from the gauge group of the standard model, which is spontaneously broken. So they are not in the same pace. And one problem is that in the standard model, the neutrinos doesn't have mass. So we know from experiments that from neutrino oscillations that the neutrinos have mass, and these masses are small. Okay, so those issues can be addressed by the left-to-right symmetric model, which is the model that we are working on this presentation. Okay. So what the left-to-right symmetric model can provide? It provides a natural introduction to the right-handed neutrinos, because the right-handed neutrinos are introduced in doublets. So we have, I'll show you later that the right-handed neutrinos show in doublets, in the right-handed doublet. They introduce a type 2 seesaw mechanism to explain the small masses of neutrinos. So we have right-handed neutrinos that in a large scale, and it explains the small scale of the left-handed neutrinos. Okay, and we have a parity restoration at high energies. So at high energies, this new model, there is a parity restoration. Okay, so this model also predicts the existence of new gauge bosons at the TV scale. We have charged WR plus and WR minus gauge bosons, and a neutral ZR, okay? And we are going, in this work, we impose limits on those gauge bosons. So I'm gonna talk a little bit about the model. It is based on this gauge symmetry SU2 left cross SU2 right cross U1 B minus L. This B is the baryonic number, and L is the leptonic number. The covariant derivative related to this model is this one. We have here the coupling GL, which is the same coupling of the standard model. We have a new coupling GR, which is the coupling that we are going to run in those scenarios that I'm going to show. And we have the coupling GBL. Okay. So the content of fermions of this model is given by this. So we have here the quarks, the leptons, and especially we have those distributed in doublets. So we have here, for example, the doublet for the right-handed fermions. We have the right-handed neutrino alongside with the right-handed leptons, and they are doublets under SU2 right, and we have doublets under SU2 left as well. okay? So that's where the right-handed neutrino shows up in the model. Okay, so in this model, the symmetry is broken by triplet scalars, and it generates mass for the particles of the model. We have here a bidoublet and two triplets. There are, one of them is triplet under the SU2 left, sorry, and the other is triplet under the SU2 right. And after diagonalize the mass matrix, we have the masses for the charged and neutral gauge bosons. So we have here the mass of the W, which I call WL, which is dependent on the GL and the V. This V is the V for the standard model, so 246 GV, and GL, as I said, is the same GL, is the same as the G of the standard model. We also have a new W, which is the WR, which depends on the GR and the VR, which is a parameter that appears when it appears in the triplet, in the right-handed triplet. Okay. We also have the mass of the Z, which is the same as the standard model, and the mass of the ZR, which depends on the GR and VR. So the fixed parameter here are the Weinberg angle and the GL, and the parameter that changes are the GR. Okay. So the idea of this paper is to impose limits on the ZR boson. Okay. And using these limits, we impose indirect limits on the WR boson. Okay, so the channel of interest is PP going to ZR and decay into dileptons. This channel, we use the narrow width approximation, which means that we are considering only cases that the ZR are produced. Okay, as I said, we impose limits on the ZR boson using dilepton data from Atlas Run 2. That works on 30 TeV of energy of center of mass and 139 phantom mass. And for the simulation, we use Fein rules to simulate the model and MATGraph. Okay. The analysis consider the mass of the ZR boson and the coupling GR as free parameters, and we consider also cuts, cinematic cuts on the pseudo-rapidity and PT of the final state particles. Okay, so as I said, we are going to impose indirect limits on the mass of the WR boson, and those limits comes from this equation here. So we have here a relationship between the mass of the WR boson and the ZR boson. They are only related to using those parameters here. The only parameter that changes is the GR parameter. So when we know the GR parameter, we know the mass of the ZR, the limit, we can impose a limit on the mass of the WR. This is important because normally when we work on left-right symmetric models, the limits that are most important are the limits on the WR mass, because the WR mass is lower than the ZR mass, usually. And it means that we can find the WR mass with a lower center of mass energy. But I'm going to show you that the limits under the ZR mass are also important because the channel is cleaner, we have dilepton data, and because the region of the parameter space for the WR mass can be improved using limits using the limits we found for the ZR mass. Okay? So here we have two graphs. In the y-axis we have the cross-section using the narrow width approximation. So we have the cross-section for PP going to ZR times the branching rate of the ZR decaying to dileptons, electron mu. Okay? In phantom bars, and in the x-axis we have the mass of the ZR boson. We consider three cases here. The GR equals to 0.55, the GR equals to 0.65, and GR equals to 1. This blue line is the line of the atlas. We have the cross-section for the atlas. And this dotted line here, we extended this line of the atlas to have a better constraint for masses above 6 TeV. Okay? So the limit that we are going to impose when the line of the simulation, which are the purple, the green, and the yellow line, crosses the line of the atlas, we have a point, and to the left of this point, the model is excluded because we overproduce the channel that we are interested in, and to the right-hand side of the point of crossing, we have the model is not excluded. Okay, so in the right-hand side we have another plot. In the y-axis we have the cross-section, and the x-axis we have the GR. As you can see, when you go to lower GRs, specifically in the 0.35 GR, the cross-section explodes, goes to infinity. This is because of this Lagrangian here. This Lagrangian is the Lagrangian that represents the interaction between the ZR boson and the fermions. As you can see, this coupling in front, when the value of the GR goes below a certain point, this point is 0.35, this diverges. So it overproduces fermions, basically. It overproduces, and the cross sections goes up. Okay, so this limit is gonna change the limits that I'm gonna show in the next slide. Okay, and we use 3 benchmark points for those cases. Okay, so this is the limit for the ZR mass. In the y-axis we have the GR, and the x-axis we have the mass of the ZR. As I said, when you go to lower GR values, there is an overproduction of the channel of interest. That's why the limit gets stronger for lower GRs, and the limit also gets stronger for higher GRs of the order 1. Okay, that part to the right is the extrapolation, and normally, though the study of left-right symmetric models uses GR equals to GL, which is around 0.65. So for this case, we have a limit around 5.2 and 5.4 TV for this specific case of GR, which is GR equals to GL. Okay? So we have also the connection with the WR mass. We have here in the y-axis the mass of the right-handed neutrino, and the x-axis is the mass of the WR boson. We have limits produced using the channels PP going to WR and decaying to electrons and jets, and dimuons and jets. So this is the green and blue limit. And as you can see, we use this equation, as I said before, which is a relation between the mass of the WR and the ZR masses. And we use the limits that we found earlier to impose this new limit here, which is this region of the parameter space. This is important to notice that in this case, we consider GR equals to GL. That's because those limits, PP going to WR and going to dileptons, were found using this scenario, okay? And it's important to notice that those limits, normally, they impose limits in the region of the parameter space where the mass of this WR is greater than the mass of the right-handed neutrino. But if we use limits found for the ZR, we can also restrict other areas of the parameter space, for example, areas where the mass of the right-handed neutrino is greater than the mass of the WR boson. So basically the region above this dotted line, okay? So we can limit other parts of the parameter space which are not limited using normal searches for WR bosons. Okay, and the limit that we found for this case is that the mass of the WR boson is greater than 3.18 TV. So, to conclude, we updated the exclusion limits on the minimal left-to-right symmetric model using Dilepton data. The GR, in this case, varied in order to explore cases beyond the usual GR equals to GL case. We use complementarity between the WR and ZR limits searches. And the implications were that the limit on the mass of the ZR is around 5 to 6 TeV, and the limit found for the mass of the WR is a limit above 3 TeV. And the take-home message is that the search for left-right symmetric models can't be restricted only to the searches for the WR boson. It can be improved using resonance of ZR bosons as well. Okay, so thank you.
Okay, thank you. Any questions?
Hello, thank you very much for your talk. You can also have limits from digest searches on these left-right symmetric models, right? Because the WR can decay back to jets. But you are not showing those, right? Digest. So that's my question. What part of the parametric region more or less cover digest searches? I'm thinking if the WR decaying back to jets.
I see. So we haven't studied this case. We only studied dileptons because of the Atlas bounds. But I don't know exactly.
Dileptons is a clear such, so we don't have that much background, only Drawian. I think that's why we have stronger bounds on dileptons. Yep.
I have a question. Ricardo, tell me if these two jets, they are boosted, they are produced in a boosted regime with high PT or not?
As far as I know, they are not boosted.
Okay.
The Atlas is only high invariance mass on the dileptons.
Okay, thank you.
Yep. Any more questions? Any questions online? Okay, I don't think so. So let's thank Ricardo again.